Live from Earth, it's Space Radio. I'm Paul Sutter, astrophysicist at Stony Brook University and the Flatiron Institute. And for the next half hour, your agent to the stars. We've got an amazing show for you. That's right, you. Today, where we're going to be talking about the latest results from the Dark Energy Survey, or DES, as we like to say in the astronomical community. This show lives on listener questions. We record every Thursday at 8 p.m. Eastern here at Spaceman Studios in New York City. So leave a voicemail to get yourself on the air. You can also follow along with our Space Cadets tuning in live from around the world, including, but not limited to, I've got a list here: Columbus, Ohio, Portsmouth, UK, Orange County, Wolverhampton, UK. That's not a real... London, UK, Pell City, Alabama, San Juan, Puerto Rico. Yes, Wolverhampton is a real town. I know it's making a joke. Howell, New Jersey, Indiana, Tucson, Arizona, Dunham Springs, Louisiana, Washington, D.C., and Duluth, Minnesota, and Austin, Texas, checking in at just the last second, and more from around the world. Hello, Space Cadets. Welcome to the show. Remember, you can go to spaceradioshow.com for all the links, a place to contribute to the show. Podcast, if you're into the podcasting thing, live stream locations on Twitch and YouTube and Facebook, all over the internets for your enjoyment. Now, the news. Milwaukee, Wisconsin. Now, that is a cheese-loving town if I ever knew one. Now, the big news that I want to talk about this week, let me pull up a screen share for you guys. Tuning in live. If you're listening to the podcast, what you're hearing is the sounds of me trying to get my laptop to work to show some little movie stuff while I'm talking about the dark energy. So, Dark Energy Survey. All right, you got a big telescope. The Victor Blanco Telescope in Cerro Tololo Inter-American Observatory in Chile. 4-meter telescope. That's like 12 feet across. That's huge. That's bigger than this room. That's bigger than Spaceman Studios. You got this big telescope. It does a survey. What does it survey? Galaxies. It takes pictures of galaxies. It finds their location on the sky, and it measures the distance of the galaxy, and then does all sorts of things. It like maps the shape of the galaxy, the color of the galaxy. Like, it makes this massive database of galaxies. In total, the survey over the course of 6 years covered 1/8 of the entire night sky, captured somewhere around 225 million galaxies, which is a lot. Let's be honest, 225 million galaxies is a lot of galaxies. It's less than 0.1% of all the galaxies in the observable universe. But hey, we're getting started here, folks. We're just getting started. This is by far the largest galaxy survey ever completed. It involved so many people. We're talking 7 different countries, 25 different institutions, over 400 individual scientists working on this, mostly graduate students and postdocs, which I saw an interesting quote from one of the leaders saying, "Oh, wow, it's cool that there's so many young people involved. They're training in astronomy right here by developing the largest galaxy survey ever made." I would counter with that statement was, do any of these young people have prospects for a job? Or are you just using, short-term young scientists to get the actual work done and then you're just going to kick them to the curb? But that's the subject of my book that's coming out either later this year or early next year, as soon as we get a confirmed date from the publisher, called A Sickness in Science. But that's not what I'm going to talk about. I'm going to talk about DES, the Dark Energy Survey. Now, I used to be based at The Ohio State University, and OSU, or TOSU, is big into the Dark Energy Survey, one of the main collaborative partners. So I wasn't personally involved in the Dark Energy Survey or any of the development. I personally have a thing against large collaborations. Maybe it's because I don't work well with others. I don't know. But there was a lot of talk. So I was there when it went down, when the Dark Energy Survey was doing its thing. And now they've released results. the survey ended back in 2019, but it's taken them 2 years to chew through the data and actually do the analysis. And they've done a release of the first 3 years of data. So we've got more to come from the Dark Energy Survey. And what did we get with our giant telescope? Our 6 years of observing, or 3 years of data that we're including with this, our 400 scientists, our 25 institutions, our millions of dollars. We got what we expected. We got a giant map of galaxies, which is super cool. And we got use that giant map of galaxies to try to understand what the universe is made of, how it's evolving, what are some key cosmological parameters that we use in our models of the evolution of the universe. And you know what? It's all the numbers we had before. Yeah, deliberate, awkward pause here. It's worth questioning. Now, the Dark Energy Survey, awesome science. They had to develop so many techniques to deal with these massive data sets, to do a good job with it. Cross-correlation biases. This is real science. There are 29 papers with this data release, and you read through the papers, and it is like the guts of astronomy. It is statistics, it is bias, it is inference, it is blinding, it is everything. And at the end of the day, we didn't learn anything new about the universe. At least on large scales, at least when it comes to cosmology. We learned a lot about galaxies for sure. And we're going to be mining this data set for decades to come. But when it comes to cosmology, we didn't learn anything new. There is one particular measurement that I see people talking about. In fact, we got a question here from RR. There are a bunch of headlines. Yeah, Zero Skull. The universe is basically the universe. That's what we learned. There are a bunch of headlines saying the Dark Energy Survey showed that Einstein might be wrong. And RR is asking, how would Einstein be wrong because of this new map or this new survey? Oh, hey, you guys, I forgot I was screen sharing. There you are. There are your questions. Hi, Nancy. Copying over the questions over on the Slack channel for me. So here's what's going on. And I just wrote an article about this for Live Science, and it should be out soon. All the measurements of all the numbers, like the age of the universe, the amount of dark matter, this and that, lined up with measurements we already had from years past. So we really didn't learn anything new. There was nothing really improved. There were some slight improvements on some of the numbers because, of course, when you get 200 million galaxies involved, you get better statistics by a little bit. One of the numbers called S8 stands, or it doesn't stand for clustering. It's a measure of how clumpy the universe is. So you have this single number. If S8 is really high, the universe is very, very clumpy. Like all the matter is condensed into very tight pockets. And if S8, is really low, then all the matter is like super loosey-goosey. Previous measurements of S8 had it at around 0.82. The units don't matter here. And the measurement that came out of Dark Energy Survey was like 0.76. So a little bit off. If this discrepancy holds true, there is going to be a tension here between measures of S8 that we get from other cosmological probes and measures of S8 that we get from the Dark Energy Survey, which could point to, maybe we need some new physics. Maybe we need to update our models of cosmology. The unfortunate thing is one of the lead scientists involved with the Dark Energy Survey gave a quote that said maybe Einstein is wrong. And then once you tell a journalist that Einstein might be wrong, that's going to be the headline. So that's what got copied everywhere. Because one scientist happened to say, hey, Einstein might be wrong. But it's not really about Einstein here. It's about cosmological measurements, and there's a lot more to cosmological theory than just Einstein's general relativity. And yes, these two estimates of S8 are a little bit different, but they're within each other's error bars. It is not a statistically significant difference. It just isn't. For the statistic nerds out there, they're different by 2.3 sigma, which is like nothing. That's I don't know, that's a fluke. That's a smudge on the paper. That is barely even worth mentioning in the actual dark energy survey results. They barely mention it, but that became inflated because honestly, and I'm not trying to detract from the actual science here and all the amazing scientists that worked on it, basically that's the only interesting result that came out. Like to the wider community. I mean, if you're a galaxy measurement survey nerd, and you know, I am, there's all sorts of interesting things, but to the wider cosmological community, the wider astronomical community, to the general public, that was like the only interesting thing to come out. Otherwise, it got us measured the universe as we already understood it and really didn't deliver any new major breakthrough insights. And so CDP is asking, what was the purpose of DES? Well, the purpose was to make the world's largest galaxy survey. And we're at a funky state when it comes to cosmology. And that's a great question, CDP, because the funky state we're in with cosmology is, and we've been here for like 2 decades now, is we don't understand most of the universe. We know that 95% of the universe is of a form unknown to physics. We don't know what dark matter is. We don't know what dark energy is. In order to attempt to try to understand what is dark matter and dark energy, we're trying to measure their effects and their properties better. So we're doing giant galaxy surveys. So we're looking at supernova. So et cetera, et cetera, et cetera. What we're hoping is that we get some measurement somewhere that is off of our predictions. Then we can latch onto that and use it to develop new models of physics, new cosmological models, a better understanding of what dark energy and dark matter is, and go from there. But what keeps happening, and so dark energy survey, all these massive cosmological surveys are just like shots in the dark, pun intended. They are trying to find and hoping to find something different. Like, okay, we ran in DES rests on, comes from another survey, the Sloan Digital Sky Survey, which was a giant galaxy survey. We didn't see anything new or different or weird with the Sloan Digital Sky Survey. So they said, let's do it again, but bigger. And maybe something interesting will pop out then. And guess what? We did it bigger and not much interesting has popped out in terms of cosmology. This kind of slowly doing what we did before, but even bigger, is very, very attractive from a funding standpoint, because the Sloan Digital Sky Survey measured this parameter to within 20% accuracy, and the Dark Energy survey will measure the same parameter to 10% accuracy. That's very, very easy to sell to funding agencies, so I'm not surprised that these kinds of surveys get funding. The hope is that as you try to measure these properties of the universe to finer and finer precision, something interesting will pop out and we gain new understanding. Nothing interesting has really popped out. Hank Scorpio has asked a very dangerous question for this show. Is Avi Loeb right about everything? Okay. Avi Loeb, who might be the arch nemesis of space radio, I don't know, is not right about everything. He's wrong about a lot of things, which we have discussed extensively about the things he is wrong about. One thing he does make a solid point about, I read his book, by the way, Interstellar, Interspecies, whatever it's called. I read it. It was honestly a bad book. I wrote a review about it. And as soon as the review is out, I'm going to let you know, and I'll probably read the whole thing out loud here on this channel. One point that he tried to make was that scientists are very conservative and that they don't want to make like wild, imaginative, crazy leaps. They would rather just do what they did yesterday, but more of it. This I see as and I do write about this in Sickness and Science. I do write and discuss this. I see it more as an issue with funding and relationship with the public, where we're trying to sell our science to the public, into policymakers, into funding agencies, and the general field is risk averse. The counterpoint, I would say, to Avi Loeb's claims that scientists are too conservative is usually when he complains about that, he's just whining that scientists aren't interested in his particular ideas. Because Avi Loeb has served on steering committees grant selection committees. He's a very, very powerful, for a long time, for like 20 years, he was the chair of the Harvard Astronomy Department. He's a very powerful person in astronomy. I haven't really seen a lot of evidence for Avi Loeb pushing for funding for projects that he is not particularly interested in. So is it a matter of scientists are too conservative, or scientists just don't like Avi Loeb's personal ideas and don't want to sign up for his agenda and let him be in charge? But this is not a show about Avi Loeb. This is not a rant show. That's the Dark Energy Survey. There are a whole bunch of questions here over on the voicemail that I do want to get to. Remember, you can leave a voicemail to join the conversation or catch the live streams on YouTube and Twitch. Go to spaceradioshow.com. And this, I need to remind you, this show is brought to you by you. It is your support that keeps this show going. It really does. It's patreon.com/PM Sutter. That's P as in Paul, M as in Matthew, Sutter, like butter, but with the S. Patreon.com/PM Sutter. If you're listening now live on YouTube, you can drop a super chat anytime you want, and you can contribute immediately, and I will give you a shout out because I really appreciate it. Dave Curtis, welcome from New Zealand, tuning in late. Better late than never. Let's listen to a voicemail. This is gonna be fun. What do we got here? What do we got? Cordelia, like that name.
Why does space not have air?
Cordelia, hello. Wow. Great question. I love your question. One of my favorite things is when kids ask questions on this show, because kids have the greatest questions. Why does space not have air? Whenever someone asks me a question like, why is something this way? Why is something not this way? I like to flip it around and ask another version of that question. So when you ask, why doesn't space have air? I'm going to ask, why does the Earth have air? The Earth has air because we have gravity. We have this giant ball of rock that we call our planet Earth. The giant ball of rock has really, really good gravity, enough to keep us on the ground, enough that we need giant rockets in order to get away from it. So it's really, really good at pulling on air molecules and keeping it close. But the farther away you get from Earth, the weaker and weaker that gravity gets. And so the Earth, all planets are able to suck up all the air and keep it all close. They're hogging all the air and they're not sharing it with anything else. So that when you go out into space and you're far away from the Earth took all the air. Venus took all the air. Mars took some of the air. That's more complicated. But like Jupiter and Saturn took all the air. All the planets use their gravity to pull on the air, and then there's nothing left for space. And so it's just a vacuum. Selfish planets. We don't like it. We've got so many questions here. Let's go to Christopher S. Let's go. Planets are greedy, that's for sure.
I have a question about black holes. So we know black holes to be infinitely dense, but this has been keeping me up on a night. Black holes are made from a finite amount of matter with a finite amount of density. Mm-hmm. How can you take finite amounts of things and turn that infinite? Is it possible that there's basically an error in the theory? Not sure. I can't figure this one out. Thanks.
Yeah, you and me both, Christopher. Excellent question. So to turn the finite into infinite, what you have to do is you have to reduce the volume. If you take you, and we're going to use this for the example, you have a certain density, you have a certain mass, you have a certain volume. If I were to squeeze on you and squeeze you together, you would have the exact same mass, but a smaller volume. Your density would go up. And if we were to squeeze you and squeeze you and squeeze you and squeeze you, your density would keep on going up with same mass, smaller volume. That's what's happening in a black hole. You're taking all that material and scrunching it down into a tiny volume. Now, in general relativity, this process continues all the way until all the stuff that did create the black hole and eventually fell into the black hole squeezes down to be an infinitely tiny point, like a literal zero-dimensional geometric point. And so if you take matter, mass, and divide it by zero volume, you get infinite density. This is incorrect. Our picture of what happens at the center of black holes is wrong. It is not infinite density. Nature doesn't make infinite densities. That's nature saying you're doing it wrong, but we don't know what the right answer is. And so we're stuck. Let's move on. Let's do another one. This is fun. How about Dawn?
We hear that Mars lost its magnetic field when its iron core solidified. And we also know that on this planet, scientists use ancient lava flows to track the orientation and reorientation of the magnetic field of the Earth. So why is it that when a planet's magnetic core freezes, it doesn't freeze the magnetic field in place instead of losing it?
Oh, that is another wonderful, fun question. So we're going to separate two things. We're going to separate the magnetic field that's being generated by the core of a planet and the effects of that magnetic field on other stuff. So you have the core of a planet. It's all hot. It's all molten. It has to be moving in order to generate a magnetic field. You need moving charges. You need them wiggling around. And so you have this massive molten core. It is spinning. It's generating a strong magnetic field. Now, this magnetic field, there are certain minerals and metals that are called ferromagnetic, which means you can use an external magnetic field and imprint a magnetic field on that material. And then that material will generate its own magnetic field. And it can do that for a very, very long time, essentially forever for the timescales we're talking about. So this is, if you have like a magnet, it has a magnetic field of its own. It's caused by all the little molecules and atoms inside of the metal, all aligned, spinning in the same direction. So all their little tiny atomic level magnetic fields all contribute together to give you this big magnetic field, a macroscopic magnetic field. So you can take a magnetic field and you can imprint it on certain materials. But when you have a core of iron and it is rotating and molten and generating a magnetic field, when it cools off, when it solidifies, there's nothing external to imprint a magnetic field on it, and it does not have the right properties anyway. You can't play this magnetic imprinting thing on anything you want. You can't do it on a wooden table. You can't do it on your brain. You can do it temporarily. That's called NMR, but that's a different thing. You can't do it on water. Like you could only play this imprinting a magnetic field on certain materials, not cores of planets. So that when the core shuts off, that is the dynamo mechanism that is generating that magnetic field. And once it shuts off, it shuts off. Now, there might be rocks on Mars that are ferromagnetic and might retain a memory of that original magnetic field, probably not over billions of years, but hey, it's not out of the question. That is a fantastic question. Speaking of questions, let's go back to the Space Cadets. And Rob Bowman is asking, has this data from the Dark Energy Survey shed light on the slightly different age estimates of the universe? So we've got this great tension in the estimation for the age of the universe. Also, the expansion rate of the universe is the same thing. One set of measurements where we do deal with early universe measurements disagrees with measurements we're taking in the present epoch. We're not exactly sure what's going on. I think it's a data analysis thing, but we're not sure what's going on. Rob is asking if the Dark Energy Survey is shedding some light on that. No, because the dark energy survey is not measuring the expansion rate of the universe directly. It's more focused on the amount of matter in the universe, the distribution of matter, the clustering of matter. It's more of a structure survey than an evolution of the universe survey. It does provide some information because you can take those parameters and feed them into a cosmological model and like try to get the expansion rate, et cetera, et cetera. And from what I've read, it looks like it leans more towards the early universe side of things, but it's not a very precise measurement all on its own. Nancy is asking, were there any spectroscopic observations made as a part of the DES? Yes. In fact, I don't know what percentage of those galaxies have spectra, but the vast majority do. Remember, this is coming on the backs of the Sloan Digital Sky Survey, which was hundreds of thousands of galaxies, individually mapped spectra. And of course, they're going to build a database, and of course, it's going to be public once they're done processing it. It's going to be a huge data set that will probably be open to the public. Like my work on voids, I was not a part of the Sloan Digital Sky Survey with those hundreds of thousands of galaxies. My own work relied on public data releases. CDP is asking a nice follow-up. Do you think that the frontier for new knowledge about cosmology is in particle colliders or in telescopes? Well, the particle physicists aren't exactly having a great time either because they built this giant Large Hadron Collider to do two things. One, find evidence for the Higgs boson, and two, find evidence for supersymmetry. Well, they got one. They got the Higgs boson. They found absolutely no evidence for any new particles, any new forces, any new symmetries. They're stuck. They're looking to the cosmologists and saying, hey, anything from the Big Bang? You got anything? And now the cosmologists are building bigger and bigger surveys and not really finding anything new. And we're turning to the particle accelerator people and saying, hey, do you have any new particles? You spot anything? It's like everyone's kind of stuck. It'll be interesting to see where the field goes over the next 10 or 20 years, because if we just keep being stuck and we keep spending more and more money and all we get is more precise measurements of stuff we already knew, there's going to be a general lack of excitement in the field. And young scientists just aren't going to become high energy particle physicists or cosmologists because they'll have more interesting things to work on. Tom Bach, is the amount of measurement that Dark Energy Survey maps statistically enough to broadly apply to the remainder of the unmeasured universe? Yeah, basically. It's a relatively broad survey, but also pretty deep. Like I don't know how far back in time it goes, but it goes pretty far. And it's big enough chunk of the universe that it reaches what we call the homogeneity scale, where one chunk of the universe is pretty much like any other chunk of the universe. Now, speaking of chunks, I have today's cheese brought to us by our good friends at Dom's Cheese. That's DOMS cheese.com. Yes, they deliver. Yes, they ship. If it doesn't say it on the website, just give them a call. They put together amazing looking charcuterie platters. They're so mouth-watering. They do catering. Like help them out. Like they're a cool local place that are getting some very interesting cheeses from around the world. And I'm privileged enough that they get to share it with me. And today we have from La Gruta del Sol, a tres leches. Now, some of you may be familiar with the tres leches. It's cake, which is delicious. But this is the tres leches cheese. It's made by combining cow's milk, ewe's milk, and subtle amounts of goat's milk. I love this description. This is from the website La Gruta del Sol. To create a unique flavor profile that is pleasing for all sophistications of cheese palates. Now, that's a weird phrasing because I don't know where I am in the sophistication spectrum of cheese palates, but tres leches apparently is for me no matter what. During the aging process, this natural rind cheese is washed routinely with extra virgin olive oil. That's always a bonus to help provide a depth of flavor and creaminess not found in other Spanish cheeses. I love it when cheese descriptions get a slightly, judgy of other cheeses. And like a little bit of cheese snobbery baked into the description. Like, oh, you won't find this in other Spanish cheeses. I don't know why the Spanish cheese had a French accent. That doesn't matter. I am unveiling this Trace Leches. Very lovely rind. You can tell it's been washed with a lot of oil. Nice coloring on there. Like I gotta try this. You know I would. Again, that's domscheese.com. Thank you so much, Dom's Cheese, for providing it today. Whew, I think this is gonna be good. I mean, how could it be not? Because a cheese made from any one of those milks is gonna be good. So here's what this cheese is doing for you. It's an amazing cheese. Very subtle notes. Very creamy, very rich. You get like waves of like saltiness, and then it goes away, and then earthiness, and then it goes away, and creaminess, and it just kind of hangs on. So you get all these notes. Nothing is overpowering anything else. Thank you to Stiff Corn Socks for the super chat. Here's what this cheese, what it does in your life. Sometimes you want to go on a cheese adventure where you want your mouth to just explode, like a cheese grenade goes off in your mouth with like some flavor or essence or aroma. Sometimes you want to go straight like Monterey Jack. You're just eating cheese for the sake of eating cheese. Sometimes you want something that isn't going to be a grenade in your mouth, but is also going to be very rich, and where it's not too subtle that you can eat a half pound of it. Don't judge me. But not too strong that you have to take like tiniest little bites just to appreciate the flavors. This is that cheese. This is the cheese. It's not your daily driver. It's not a Porsche. This is the cheese that when you go on vacation, you rent a car that's like a little bit special. That's this cheese. This is the special rental car of cheeses. And it deserves a spot on your plate and also to be in your mouth. Thank you so much. Remember, this show is brought to you by you and by Dom's Cheese. Patreon.com/PMSutter, or drop a super chat in the chat right now. I really do appreciate it. Thank you, Nancy Graziano, for producing the show and wrangling the Space Cadet. Catch the live stream every Thursday at 8 p.m. Eastern. Visit spaceradioshow.com for all the links. And of course, thanks again, Earthlings, for listening. See you next week. And remember, science is for sharing. End of transmission.